Hello everybody, this is Mr. Canfield. I'm going to be going over the mixed questions number 1, which is our review packet for the post-test coming up. And then if there's time, I'm going to go over more of them. So if you have a hard time reading any of these, just remember that we gave the packet to you in class, so you should be good. I'm stumped, I don't know. Okay. So it says graph the function f of x is equal to x squared minus 4 over x plus 4. For this graph, list all the asymptotes, vertical, horizontal, and slant, and find the x and y intercepts, or explain why you cannot. So let's see, vertical asymptote, if there is one. So the way that we handle this, x squared minus 4 over x plus 4. Let's see how that's showing up. Okay, showing up well. So remember that vertical asymptotes, the big idea is we look at any domain problems that we have. So we look at our denominator and our x plus 4 in the denominator. We wonder, hey, is there an x value that makes that equal to 0? And sure enough, negative 4 makes that equal to 0. So we have a potential asymptote when x is negative 4. The only thing is we have to double check and make sure that it doesn't cancel out with anything in the numerator. So let's see, if the numerator says x squared minus 4, well then that's the difference of two perfect squares, and I could rewrite that as x minus 2 and x plus 2. That's how the difference of two squares factors. And so x plus 4 doesn't cancel with either one of those. And so because of that, I can say that my vertical asymptote is x equals negative 4. And just a reminder, the way that I got that negative 4 and not regular 4 is it was what number is going to make that 4 cancel. A 4 plus 4 gets us 8. It doesn't cancel, but a negative 4 will. And so I can now go up to my graph. Notice how I didn't look at this in the calculator yet. I'm just kind of going off of the numbers. So because of that, I'll go to negative 4, and I will draw a dotted line indicating an asymptote. Boom, there we go, okay. So then we'll move on to part B. It says horizontal or slant asymptote. So the way that we check for the horizontal asymptote, this trick that I show my students, so whether or not you remember it from, September, October, I can't remember. We did this a long time ago. But the way that we found horizontal asymptotes was we looked at the biggest power of x that we see anywhere in the problem. And the biggest power that we see is x squared. So on the top, so horizontal asymptote, on the top we have 1x squared. On the bottom, I don't see an x squared on the bottom. So on the bottom we have 0 x squareds. That x is not big enough. We need an x squared to match up with that. So the way that we do this is we do 1 divided by 0 and we see what we get. And just a reminder, if you're not sure what 1 divided by 0 is, or if you thought it was 0, it means that your brain mixes this up sometimes. And since we're allowed to use the calculator on this, use the calculator. 1 divided by 0. Oh, I'm not allowed to do that. Right. So because of that, it's undefined. There is no horizontal asymptote, but there may be a slant asymptote. So if you're in CP right now, we did not go over this year. I'm going to talk about it for those of you who want to know how to do this. So the way that we would approach the slant asymptote is we're going to do long division here and see what we're left with. So if I go through and I do long division, so I'll put my x plus 4 out front. And when I do long division, I like to write this out. So x squared, instead of writing minus 4 here, I'm going to put plus 0x as a placeholder to help me. And then my minus 4. Because doing long division like that really helps. It helps me from skipping necessary information. It helps me line up my place values. All right, so I ask myself, how many times does x go into x squared? And it goes in a total of x times. So I can put an x up top. And then we're going to take x times both of those. So x times the x gets us x squared. X times the 4 gives us plus 4x. And remember then that we're going to go in and we're going to be subtracting. So I'm going to do x squared minus x squared plus 0x minus 4x, because that's a plus already, so it's going to change to a minus. And so because of that, we're going to have those cancel. 0 minus 4 is negative 4x, and then minus 4. And then we need to find out how many times does x go into negative 4x. So x times negative 4 gets us negative 4x. So it's going to be x minus 4. And I'm pretty sure that's all we have to do for the slant asymptote. Let me just double check. It's been a while since I've done slant asymptotes. I mean, I totally did this beforehand, and I'm just rehashing it. I'm not doing this blind. All right, so if I hit graph, oh, I'm super glad this happened. So somebody was doing who knows what with this calculator. I'm gonna push zoom and go down to standard. So again, push the zoom button, it's right there. I should point with a different finger. Zoom, go down to standard. Sure enough, oh, I only see part of this. If I do zoom fit, it'll zoom out a little bit. It'll make it so you can see the whole graph. So we have our, if you look here, 1, 2, 3, 4. We've got our vertical asymptote at negative 4. I'm going to go back to standard so that we can kind of see the slantiness a little bit. See how it's kind of going up like that? So that slantiness should mimic this x minus 4 line. So if I go in and, I think that's the first time I've ever done that while filming. All right, let's see. X minus 4 accidentally cleared out that whole row. So if I look at the original, it should approach, yeah, okay. You can see that it's kind of getting close to that slant asymptote. And if we shot the x value out to 100, we'll see that they get really, really close to each other. So good to know. So my slant asymptote, it needs to be the equation of a line. So I'm going to write y is equal to x minus 4. Okay. So there was not a horizontal asymptote because there was a slant asymptote. Remember, slant asymptotes can only occur if the top is 1 power greater than the bottom. All right. Y-intercept, if any. Remember, y-intercept means plug in 0 for x. And x-intercept means plug in 0 for y. Okay, so if I plug in 0 for x, for y-intercept, that would be 0 squared minus 4 over 0 plus 4. And however you want to do this, you can do this. 0 squared is 0, minus 4, we get negative 4. And then there we get 4. And so negative 4 divided by 4 is negative 1. All right, so depending on who you are, some people are okay with negative 1, just saying the y-intercept is negative 1. I'm going to write the y-intercept as the actual point that it is, though. Remember, I plugged in 0 for x, so that means that in my coordinate, x is 0, and my y value is negative 1. All right, so x-intercept, if there are any. And so for x-intercepts, all we have to do is we plug in 0 for y. And so we're going to say, remember that f of x is actually equal to y, like that. It's the same idea. So we're going to wind up saying 0 is equal to our function. So 0 is equal to x squared minus 4 over x plus 4. But what I'm going to do is I'm actually going to use the factored version. That's going to make life easier. So 0 is equal to x minus 2 times x plus 2 all over x plus 4. So if I'm trying, now I need to solve this. That's the tough part. Unlike our previous one where we plug it in and get a number, this time we plug it in and now we have to solve it. So the way forward here is, the short version is you can ignore the denominator because the denominator will never make this fraction equal to 0. Dividing by a number never made something equal 0. Don't believe me? Just show me. Find it. Pick a number, divide by something else, get 0. You won't. It doesn't happen. It never happens. And so I can ignore that. The other way that we could more mathematically handle that is multiplying both sides by x plus 4. Over here, x plus 4 times 0. Oh, it's still 0. Anyway, 0 is equal to x minus 2 times x plus 2. And if you remember how we solved these, all we had to do was set each of them equal to 0 on their own. And we say, hey, when does x minus 2 equal 0? Well, I got to add 2 to both sides to do that. I get x is equal to 2. Or hey, when does x plus 2 equal to 0? Well, I need to subtract 2 from both sides and I get x is equal to negative 2. And so my two x-intercepts are 2 comma and negative 2 comma, oh wait, I know x is 2. What's y? I know x is negative 2. What's y? We plugged in 0 for y. So it's 2, 0 and negative 2, 0. And those are my two x-intercepts for this. So I'm going to go in and I'm actually going to graph all these things. So I'm going to graph my y-intercept of 0, negative 1. I'm going to graph my x-intercepts of 2, 0 and negative 2, 0. And you should already see that this is kind of helping me draw this graph. Remember when we go in here, and I erased it because I'm so smart, but it had that swoop shape to it. So I'm going to be able to go in and be like, hey, and like, remember, asymptotes never come in contact with the actual graph. So, and the way I'm going to do the rest of this is I'm going to go and I'm going to graph my slant asymptote. So y equals x minus 4. Well, that means that has a slope of 1 and a y-intercept of negative 4. So let's see, 1, 2, 3, 4. Up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. It just continues. And so I can draw this dotted line and then have my curve like approach it. It's getting closer and closer and closer. And I'm going to cheese this a little bit. I'm guessing, because of the way my graph was, I'm guessing we're not going to be able to, so I'm going to do second table. So I'm going to see what negative 5 is. Nope, wrong way. Negative 5 is negative 21, and I definitely don't have that. So there is something over here, and it's going to be like, it's going to be something like that. But just because of the way the graph is zoomed, I don't have room to draw it. So, oh well, that's all I have room to draw. We'll see a few more of these in the other packets. So those maybe will be a little bit more helpful. All right, next one. Given f of x is equal to x plus 2 and g of x is equal to 4x minus x squared, compute and simplify your answers. All right, we want Fogg and Goff. No, just kidding. F composed with g, or f of g of x. Remember that this means f parentheses g of x. And the little x on the end is just saying we're just using x, we're not plugging any numbers in. If there had been like a 2 there, it would mean do that and then plug in 2. But anyway, compute and simplify your answers. Okay, so f of g of x, that means I take f of x and I plop it down. F of x is x plus 2. My next step is I rip out all the x's that I see. The only x I see is x, so I rip it out, keep the plus 2. So nothing's changed, right? Now I am going to drop in g of x, and g of x says 4x minus x squared. Now I can go through and do my order of operations and simplify. So the only thing I can see to do is to rearrange, because there's no number in front of the parentheses to distribute, there's no square, there's nothing fancy going on. So we're going to say negative x squared plus 4x plus 2 and call it a day. All right. Let's try g of f of x. That means write g first, throw a parentheses, then write f of x. So to handle that, I'm going to drop g of x on the counter. So 4x minus x squared. I'm going to say, hey, anywhere I see an x, rip it out. So that's going to be 4, rip out the x, write a parentheses. X, rip it out, write a parentheses, has a squared after it. All right. So this one's going to be significantly more work, because now it says take f of x and put it in each of those parentheses. So take that x plus 2 and put it in each of those parentheses. X plus 2, x plus 2. All right, so here we go. Now we gotta do our PEMDAS. So I see this 4, I can distribute that 4, I can get 4x plus 8. Then on this one, I'm gonna leave that minus sign there. Come back to that in a little bit. remember that x plus 2 squared literally means x plus 2 times itself. So when I FOIL this, x times x gets me x squared, x times 2 gets me plus 2x, 2 times x gets me plus 2x, 2 times 2 gets me plus 4. Like that. And then I can combine like terms and get x squared plus 4x plus 4. So now I'll be able to distribute that negative, get 4x plus 8 minus x squared minus 4x minus 4, because that negative is going to change all those signs. Let's see, 4x and the minus 4x are going to cancel. Then 8 minus 4 is going to get me 4. So I can say 4 minus x squared, or I could say negative x squared plus 4. That would be what we call standard form, but either are acceptable. Okay, so that's those. How are we doing on timer? It's 16 minutes. All right. So our next question says, determine whether f of x and g of x are inverse functions. Show all work. So the trick with showing whether or not they're inverse functions is we take turns plugging them into each other. So we do what we did here, except the answer has to be x both times. As long as we do what we did here and we get x and then we get x, then they're inverses. So here we go. Let's try f of g of x. So I'll take my f of x, which is square root of x plus 2, and then I rip out x. Notice the only thing that changed is x turned into a parentheses. Everything else is the same. And then I drop in my g of x, which is x minus 2 squared. And then I'm going to have to simplify this out and see what we get. So we just did x plus 2 squared a minute ago. X minus 2 squared is going to be exactly the same, except that's going to be a minus, that's going to be a minus, that's going to be a plus. You know what? Canfield, just do it. Just do it. So if we're going to do, let's see, where do I write from? If we're going to do x minus 2 squared, which is x minus 2 times x minus 2. I'll do the lattice method on this just in case you prefer that method. Just to remind you that we can do that x and a minus 2, x and a minus 2. That was where we multiply the different pieces of the box. So in this box I have x and x, which is x squared. This piece I have negative 2 and x, which is negative 2x. This piece I have x and negative 2, which is negative 2x. And this piece I have negative 2 and negative 2, which is positive 4. So then we can combine our like terms and we get x squared minus 4x plus 4. So that means over in the problem proper, we can say, okay, well then that's x squared minus 4x plus 4 plus 2. And I get the square root of x squared minus 4x plus 6. Okay, so when I take the square root of this, do I get x? This is not equal to x. So, no, they are not, I shouldn't say they, no, f and g are not inverses of each other, because f of g of x is not equal to x. So if we had gotten x there, then I'd go back and do the same thing. I start with g of x and drop f of x in, and then we need to get x. So if we get x both times, then yes, they are inverses. All right. So, my guys, we did not spend any time looking at problems quite like this, but it's an extension of what we've learned with inverses. So, just stick with me. We'll be all right. It says use the graphs of f of x and g of x, pictured in to answer parts A and B. Ooh, be careful. This one is g of x. This one's f of x. That's a little silly, but oh well. So we want to make sure we pay attention to that. It says find the value of f inverse of -1 and justify your answer. So remember that the whole idea with inverses is that x and y trade places, right? We swap x and y. So f versus f inverse. Oh, there's another spot for name. Well, I guess I'm still me. So f versus f inverse. So if I see f inverse of -1, that's saying that f inverse has the point -1 comma something, right? Well, then what does that mean about regular old f of x? Well, it has the point, instead of -1 something, it has something comma, -1 something. F has something comma -1. And so if I go to f of x and see, hey, when do I get a y value of -1? Oh, right there, right? We get a y value of -1, and that happened when x was 0. So that means that the inverse, instead of having 0, -1, it's going to have -1, 0. So find the value of that. It's going to equal 0. So now when it says justify your answer, there's a few ways we could mathematically justify our answer. We could say inverses trade the domain with the range. I'm not sure what if there's a better statement about that. Maybe ask me or ask your teacher if you want a better reason than that. Okay. Find the value of f inverse of g of -3, justify your answer. Okay, this sounds really, really bad. However, if we're careful and we take our time, it's not. Let's see, not. I said 5 knots, so those cancel. Yeah, okay, awful. So 5 knots and then awful. All right, so we see f inverse goes first, parentheses, g, parentheses, -3. So the real way to handle this is we just go all the way on the inside and then figure it out from there. So I don't worry about this little f inverse thing yet. I just worry about g of -3. G of -3 means when x is -3, what do we get for g? Well, let's see. Here's g. When x is -3, what do we get out for g? Oh, we get 0. So that means that g of -3 is 0. And so I can rewrite this as f inverse and just put a 0 in its place. So what is f inverse of 0? So I'm going to do a little table like I did before. I know in f inverse that I have 0 comma something, and that means that in regular f of x, I'm going to have something comma 0. And so I want to go find when is my y value in f of x equal to 0. So I'm going and looking at f of x, y value of 0. No. Aha, right here. So that happens when x is 1. So that means that f inverse, when instead of being 1, 0, f inverse is 0, 1. And so f inverse of 0 is equal to 1. So I think showing our work, showing where we're getting things from, I'm justifying my answer. So, all right. Given f of x is equal to x squared plus 5, restrict the domain of f of x so that the function is 1-to-1 and has an inverse function. State the domain and range for both f of x and for its inverse. So, if we look at x squared plus 5, well, remember, that's just a parabola, and that plus 5 on the end. If you don't remember what it does, go double check in your calculator. It's going to move it up 5. So I can go, okay, here we go. Here's 5, and it goes, woo, like that. All right, that's our original f of x. So we're going to make our new f of x have a domain we're going to have a domain that is 1-to-1. And another way we say that is a domain that passes the horizontal line test. So basically, we don't want this to be a parabola where boom and then boom. We don't want it to hit more than once horizontally. And so because of that, if we just focus on this half and then cut off this half, we're good to go. So instead of saying our domain is all real numbers from negative infinity to infinity, we could say our domain goes from 0 to infinity. There's more than one way to do this, but that's the way that I'm choosing to do that. And so its range then, if we look, the range, the lowest that it ever gets is 5, and the highest that it gets, well, it goes off to infinity still. There we go. So remember that in inverses, the big idea is that x and y trade places, and domain is x and range is y. So all I've got to do is say, well, okay, f inverse domain is going to be the range of the original. The domain is going to be from 5 to infinity, and its range is 0 to infinity. Now, you might be wondering why I'm not finding the inverse. Given f of x, restrict the domain of f of x so that the function is 1-to-1 and has an inverse. It does not tell me to find the inverse. I don't need to find the inverse. State the domain and range for both f of x and f inverse. I don't need to know what f inverse is to be able to tell you what its domain and range are, because I just traded those two. So it says the average price of a new car has been increasing exponentially since 1950. A model for the average price is given below, where t equals years since 1950. So it says P of t is equal to 650 e to the 0.0628 t. Use this model to estimate the average price of a new car in 1990. And so all we have to do is plug in 1990 to this equation and we'll be good. However, we don't want to use the number 1990. If we read carefully, it says t equals years since 1950. That means that 1950 is equal to 0. And so 1990, which is 40 years later, is going to be equal to 40. And so I'm going to want to take p and plug in 40 for t. So I'm going to say 650 e to the 0.0628 times 40, or parentheses 40 if that looks nicer. That looks nicer. Now, I like trying to get all the points I can on questions. I would show this before you go to your calculator. If you make a typo in your calculator and you just write your number and it's wrong, you don't get anything. But if you write out what you're going to do and then plug it in, then we're good. So, average price of a car, that means all I got to do is write my answer. 8014. Now this is money, so I'm going to stop where money stops. Money stops at that second decimal place. So say 22. That 1 gets rounded up because of the number after. That 6 tells the 1 to round up. If that had been a 4 right there, I'd leave it at 21. So $8,014.22 was the average price in 1990. In what year will the average price of a new car be $35,000? Okay, so if you forget what I'm about to do, you could literally go up here. Instead of doing 40, try 41. Gee, that wasn't enough. Maybe year 90. That's a little bit more than I want, because I'm trying to find 35,000. And you can just keep on playing around until you get it. No, that's not what you're supposed to do, but it totally works. You can keep on trying that. So I haven't done this problem before, so I'm going to guess 53. Okay, 53 is about halfway there, so let's do like maybe 10 more years. 63? 63 is almost there, so let's do like, what about 65? 65 was too much, so maybe 64. And it's just, going back and forth, just trying it over and over again. Oh, so it's going to happen in that 63rd year. And then I would just do, so 63 years after 1950. Let's do 1950, add 63 more years, you go to 2013. Yep, okay. So that's totally a way to do this. But it's not what you're supposed to do. What you're supposed to do is you're supposed to say, price is this number. So when we put the 35,000 over here, 650 e to the 0.0628, and we don't know t. And we're going to solve this equation for t. This is like the real way that you do it. So the first thing we'll do is we'll divide both sides by 650. And we'll get our 35,000 divided by 650. And we get, oh, that's a lovely number. I love that number. No, so I want to try to not have to write that on my paper. I'm going to push math enter and see if, 700 over 13. Cool. And my calculator is going to be handling all these numbers, so it's going to be easier for me to deal with that a little bit later. So e to the 0.0628t. So in case you don't remember, the way that we get an exponent down to the bottom when we have an e is we take the natural log of both sides. We're going to ln it. We're going to ln that side. We're going to ln that side. And when we do that, on the right-hand side, we get 0.0628t. And over here, we're going to get the whatever the natural log of that is. I just remembered in my class, I didn't teach you to ln both sides. I taught you to rewrite. So another perfectly viable strategy here. We have our 700. So if you're taking my class, we learned this way. We're going to rewrite this as a logarithm. So we're going to write it log base e of 700 over 13 is equal to 0.0628t. So we're going to have the exact same thing. Remember that log base e and ln are the exact same thing. The last thing we have to do is just divide by this 0.0628, which it looks really gross, but go into our calculator saying, hey, I just want to take the natural log of, wait, am I in the nice math mode? I am, okay. So I take the natural log of 700 over 13 divided by, that's not good, divided by 0.0628. Oh, I made a typo. And this, again, it's good for us to show our work. So ln of 700 over 13, close the parentheses, then divided by 0.0628. 63, so t is equal to 63.473, but I need to know what year that is, so I'm going to add that on to 1950, and we're going to get 2013. All right, sorry about that. So we added 63 to our initial year, and we got the year 2013. So notice how I was able to show my work very easily for this. Showing your work by just kind of guessing numbers doesn't really work. But hey, when in doubt, if you get stuck, it'll get you there. All right, number 7. We've got a verifying trig problem. It says prove, but remember we got rid of the word prove and we said verify, because verify it's not as scary as the word prove. And it's the same thing. Okay, so they're using these betas here. You can, if you want to replace it with an x because you're going to feel more comfortable, you can do that. Because it's the same thing. Variables are just like saying, hey, this is some unknown. So if you like using x's, use x's. Sine x over 1 minus cosine x equals 1 plus cosine x over sine x. I like to remind my students that these are like multiple choice questions. This turns into something else, and we have to pick the answer choice that it turns into. Oh, it turns into that. The only thing is we have to show the work that gets it from here to here. So I'm going to rewrite the left-hand side over here just so that I take all the space and use it well. Okay. So my guys just learned this today. We just talked about this, so it should be fresh in their brains because you're watching this video while I'm uploading it. Wait, no, never mind. Okay, so what we're going to do is, my guess is that there's some kind of conjugation that I'm going to have to do where I multiply the top and bottom by the conjugate of 1 minus cosine x. So in that case, it's 1 plus cosine x. Remember, the conjugate is always this, but the opposite sign in the middle. 1 plus cosine x. So if we do that, the top, when we distribute this, sine x times 1 gives us sine x. Sine x times cosine gives us plus sine x cosine x. And then we FOIL out the bottom. So there's a couple of ways we could FOIL it. Some people like using the lattice method or the Punnett square method. Some people like to just FOIL it. Whatever you want to do, go for that. You do you. I'll do the lattice method because I know some of my students really like using that. I know it's a little bit small, but hopefully it's still legible. So I'm going to put my 1 and my minus cosine x, and then I'm going to do my 1 and my plus cosine x. Also, if you already know the pattern, you can just write it what it is. If you understand how conjugates work and you know what this is going to get, that's totally fine. So 1 times 1 gives us 1. 1 times minus cosine gives us minus cosine. Maybe I should have drawn the box a little bigger. 1 times plus cosine gives us plus cosine. And the cosine gives us cosine squared, but it's a positive and a negative. So it's negative cosine squared x. And so these guys are going to cancel, and we're just going to be left with 1 minus cosine squared x. Okay. Remember, my goal is for this to be this. Right now, this does not look like that. And I'm like, man. So I think I can use a special formula. So the special formula, it is on our formula sheet. I see 1 minus cosine squared. And I see that in the answer, I'm supposed to have sine squared down here. So this is a hint to me that I can use that Pythagorean identity, the sine squared plus cosine squared equals 1. And there's a bunch of different ways to manipulate it. And the way that I've been doing it in my class this year is I'm saying, well, I see the 1 and I see the cosine squared. Let me replace the 1. So everything else I'm going to keep the same. Oh, let me keep my equal signs here. So I get my sine x plus sine x cosine x. We get our minus cosine squared x still is there. Now this 1 turns into sine squared x plus cosine squared x. So when that 1 turns into that, well, now when I combine my like terms, the two cosines kill each other. I mean, the two cosines cancel, and we get sine x plus sine x cosine x all over sine squared. All right. So I've run out of room. I'm going to continue down on my next column. So my next column, what I'm going to do is, there's two ways to handle this. The short way to handle this would be pull a sign out of both of those and cancel the sign with the bottom, and you should be left with your answer. I'm going to do this a little bit more long and drawn out just to kind of mimic the way that I've been doing it in my class. So I can, now that I have this, I can break this into two separate fractions, right? I can say this is sine x over sine squared plus sine x cosine x all over sine squared. And now, because of the sine over the sine squared, I can say cancel, cancel. This is 1 over sine x plus cancel, cancel. This is cosine over sine x. And so now I look and I go, okay, what is this supposed to look like? My final answer is supposed to be a single fraction where it says 1 plus cosine, and on the bottom it says sine x. So if I look carefully, I'll see that, oh, they have the same denominator, so I could recombine them and get my 1 plus cosine x all over sine x. And that equals my answer there, so we're good. So this isn't the only way to do this problem. This is a, let's see, 1, 2, 3, 4, 5, 6, 7. That's a 7-step way to do this problem. We could definitely do it faster, but I like providing ways where there's going to be consistency, and this conjugation method, being very careful to go through all the steps, hasn't steered me wrong yet. So let's see what's next. Use a summation formula to simplify and evaluate the exact value of the expression. Show all work. Give the unit circle value, not the decimal approximation from your calculator. All right, so I'm going to grab my formula sheet, and all we're going to do is look at the formula sheet. So this is one of my sum and difference formulas, and all I have to do is go, hey, formula sheet, how you doing? Oh, hey. And I go here, and I see cosine 80, cosine 50. So we would call the 80 the u and the 50 the v. 80 is still u, sine is still v. So that means that this is cosine u, cosine v, sine u, sine v. And it's a plus in the middle. And then I just go and I find my formula. Cosine u, cosine v. Oh no, that's a plus. Let's see, cosine u, cosine v plus sine v, sine u. Okay, that's the same as that's basically the same as this. Maybe I should switch these, but remember that when we're multiplying, it's okay to switch. It's not okay to switch the cosine 50 with the sine 80 over here, but I can trade this is like saying a times b, or b times a. They're the same thing. So if we do that, well then this matches up with the cosine of u minus v. So I can say this is cosine of u minus v. Well, u was 80, so cosine, I wrote CO8. Good job. So I can write this as cosine of 80 minus 50. Which, if it's not coming together in your brain yet, cosine of 80 minus 50 is the same as saying cosine of 30. Now, to those of you who know your unit circle, this is like, oh shoot, I'm done. All I've got to do now is just pop over to my unit circle and go, oh hey, cosine of 30, root 3 over 2. Oh, my answer is root 3 over 2. Done. Let's say you're having a bad day, your unit circle's not working out for you. You can always go, hey, I wanted cosine of 30. Oh, I need to make sure I'm in degree mode since I'm doing degrees. I want to do cosine of 30. Ew. Okay, I got that. Well, I don't remember what that is. Is that a half? No. Is that root? No, it's not pi. So we tried a half, it didn't work. Let's try root 2 over 2. No. So is it? Please be root 3 over 2. Oh, there you go. Okay. So I didn't tell you that though, because this is not, you're not really doing the problem. You're kind of cheesing your way there, but grades are grades, I guess. And sometimes last ditch efforts help us get through things. All right. Number 9. Okay, so I did an oopsie on number 9. So I'm going to redo number 9 from the ground up. Let's see, here we go. It says the percentage of the moon that is reflected in the night sky oscillates from 100% to 0% every 28 days. So first things first, if we kind of think about this over time, we'd say here's 0, here's 28 days, here's 100%. We'd say at 0%, it goes all the way down, or sorry, at 0 days, it's at 100%, and then at 28 days, it's going to be down here at none. So how many more days until it gets back up to 100%? It's going to be 56 days, or 28 more days, which is 56 days. So, and then we're going to be back up here. So then we got to ask ourselves, is this a sine wave or is this a cosine wave? And if you don't remember, you can always go, okay, well, which one starts out high and then comes low? And if you don't remember, just go, well, hey, so sine x looks like this. Remember, I'm looking at 0, so it goes up, then down, then up. So probably not that, but if I look at cosine, cosine goes down, then up. Okay, so you might even be able to see it, that this right here is very similar to this right here. So it's telling me that I'm going to want to use a cosine graph, and so I'm going to use my formula sheet. My formula sheet says f of, I'm writing in pencil, I guess it's visible enough. F of x is equal to a cosine of bx minus c plus d. Okay, so first things first, amplitude. So how far from here to not the bottom? Amplitude is how far to from the middle of the wave to the top or bottom. Well, if it's 100 from the top to the very bottom, then the middle is going to be at 50, right? And so that's going to be 50, and that's going to be 50. And so that means our amplitude is going to be 50. Cosine, we'll find b in a minute, x minus c. So does this start at, no, it starts exactly at 100%. This phase has not been shifted at all. So we will, we'll figure that c is 0, and then d, are we getting moved up at all? Well, remember that this is really, how far has the middle of the wave been shifted? So the wave has been shifted up 50. So now we just got to find that. Well, we know that b is equal to 2 pi over the period. So b is equal to 2 pi over, well, what's our full period? Start to end, 56 days. So I can put a 2 pi over 56 right there. Call it a day, be done that question. So, hope that helps. Matters. All right, find the domain and range of cotangent of x. Well, remember that the domain of cotangent is cosine x over sine x. And so that means that anytime sine of x is equal to 0, we have a problem in our domain. And so sine of x equals 0 when x is equal to 0, when x is equal to pi, 2 pi, etc., etc., etc. And so because of that, we can say that the domain of cotangent is actually all real numbers except x is not allowed to equal 0, pi, 2 pi, and so on. And another way that we can write that is, instead of that, we could say x is equal to 0 plus n pi. Or we can say plus or minus n pi. Because we could also go negative pi, negative 2 pi, and all those would be problems too. So its range, if you remember, it looks kind of like that heartbeat. Actually, I might have that backwards. Yeah, I got it backwards. That's what tangent looks like. Cotangent looks like that. Why am I drawing it? It's right there. It looks better. Okay. It looks like that. So our range, we can say it goes from negative infinity to infinity. Or we can say all real numbers. So remember, when we take the inverse of this, its domain is switched with its range. And so we can say that the domain of inverse cotangent, the domain of inverse tangent, we can say is all real numbers. And its range, instead of this, instead of having it cut and cut and cut and cut and cut, what we wind up doing is we just take this first block here and we say it goes from 0 to pi. Wait, it does not include those, and you can't take cotangent of 0. We just said it's a domain problem, so we'd say 0 to pi, not including those endpoints. So, yeah, if I remember correctly, that's what that is. Definitely double check with Ms. Lycon on that one. Okay, hope this was helpful. Bye.